Ever look at a dolphin fin or a bird's wing and think, wow, nature really nailed it?
It's incredible, right?
Turns out engineers are right there with us trying to unlock those secrets.
Yeah, and we're getting closer all the time.
That's what we're diving into today, bio-inspired engineering, where researchers are taking cues from nature to design some seriously cool tech.
Exactly. Things like crazy efficient underwater turbines, even aerial vehicles.
And get this, today's deep dive centers around a research paper that's like cracking the code on simulating these flexible flapping designs.
Which, believe me, is no easy feat.
Because getting those simulations right, it's like trying to predict the weather while riding a roller coaster.
It's true, the complexity is mind-boggling. You're essentially trying to map every interaction as something moves and deforms in a fluid, whether it's air or water.
Okay, so before we go full-on science geek here, let's make sure we're all on the same page. Why is simulating a flapping wing so hard?
Well, it all boils down to capturing the dance between the fluid and how the object moves and how its shape changes over time, those deformations.
So it's not just about movement, it's about how that movement changes the shape of the object, which then changes how it moves through the fluid.
It's like solving a puzzle where the pieces keep changing shape as you try to fit them together.
And to add another layer, this research hones in on a tool called OpenFOAM.
Right.
Walk us through that. What is it and why does it matter in this flapping wing simulation world?
So think of OpenFOAM like a really powerful piece of software, one that engineers use to simulate how fluids behave.
We're talking computational fluid dynamics here.
Exactly. Anything that moves through air or water. OpenFOAM can help us understand how that fluid is going to interact with it.
So this research, they tackled a specific limitation in how OpenFOAM handles these crazy simulations, right? Like it needed an upgrade.
Exactly. The team behind this developed something called dynamicOversetZoneFvMesh.
Okay, before our listeners' eyes glaze over at that name,
Right.
hit us with the breakdown. What does it actually do?
Imagine a chef with a whole set of knives, okay? This method is like giving them this super precise tool for ultra-delicate tasks. It lets researchers divide the simulation into zones and apply different types of motion to each.
So instead of the simulation treating the wing as one big moving thing, it can now say, okay, this part's rigid, this part's flexible, and model each one independently.
You got it. And that's huge. Because now we can capture those super nuanced interactions. Fluid, movement, deformation, the secrets to the efficiency we see in nature.
Okay.
Yeah.
So they gave OpenFOAM this massive upgrade. What did they do? Unleash it on a swarm of virtual birds.
Not quite, though that would be pretty cool.
Right.
For this study, they focused on a two-dimensional, flexible flapping foil.
Okay.
Picture a super thin slice of a dolphin fin.
Gotcha.
Classic bio-inspired design.
Yeah.
And the perfect test subject for this kind of simulation.
So they set this virtual fin flapping in the digital water.
Right.
What were they looking to find?
They wanted to see how flexibility impacted efficiency. So they ran simulations with all sorts of variables, changing the foil's flexibility, the speed of the virtual currents, you name it. And here's where it gets really neat.
Okay, lay it on me.
They found that just by letting the foil bend a little, its power extraction efficiency shot up by a lot.
By how much are we talking here?
32% compared to a rigid design.
Hold on. Just by letting it bend, we're talking about a third more efficient.
That's exactly it, just by adding some flexibility.
What's the magic? How does that even work?
It's all about how that flexibility lets the foil interact with the fluid more dynamically.
Yeah.
That little bit of give lets it adapt to the flow, finding those sweet spots of efficiency that a rigid design just can't.
So we've got these cool results from a simulation, but what's the takeaway for the real world?
This has huge implications for tons of tech.
Like what?
Think about it. Anything that moves through air or water could be revolutionized by this kind of design.
Give us the good stuff. What kind of real-world applications are we talking?
Imagine wind turbines that can change their shape on the fly,
Okay.
adapting to gusts and breezes to capture way more energy.
Okay, I like where this is going.
Picture underwater turbines harnessing the power of ocean currents with off-the-charts efficiency, all thanks to these flexible blades that mimic marine life.
So we're not just talking about, like, small improvements here.
Yeah.
We're talking about, like, a total game changer for how efficient things like wind power and hydropower could be.
Absolutely. This is a potential paradigm shift. And didn't stop there either.
Oh.
This has the potential to revolutionize robotics, too.
Okay, now you've got me really intrigued.
Imagine underwater vehicles that move with the agility and grace of a fish. All because of these flexible, bio-inspired designs.
So we could be talking about robots that can explore, like, the deepest parts of the ocean.
Exactly.
With crazy precision, crazy efficiency. What could we even achieve with that kind of tech?
Honestly, the possibilities are pretty much endless. We could explore the oceans in ways we never thought possible.
Yeah.
Uncover hidden ecosystems, monitor the health of the planet in real time. It's incredible.
And it all started with, like, researchers trying to simulate a flapping wing.
It did.
And now it's opening up all these doors to the future.
It really is. And we have to remember, this is still early.
Right.
We've seen some incredible things with these 2D simulations, but imagine what we can do in 3D.
So taking this research from the computer, from the digital world, into the real world, what are the next steps? What needs to happen to make that jump?
The next big thing is translating these simulation successes into real prototypes.
Right.
And that means testing materials, refining the designs, really pushing the boundaries of what we thought possible.
This research has given us a peek into a future powered by flexible, adaptable technology. It's exciting stuff. So as we wrap up our deep dive today, I'm left with one question. What other applications are out there that we haven't even thought of yet? What other breakthroughs are waiting to be discovered? Something to ponder, listeners. Until next time, keep exploring.